So what I'm going to do is I'm going to do these 2 units of scheduling, and I'll start with talking a little bit about modern architecture. So this is this lecture and next lecture. We'll see how far we can go today. And then introduce instruction scheduling, what we are doing in instruction scheduling. Talk about the most basic form of scheduling, which is called list scheduling. At the beginning, we'll talk about a very simple architecture. Then we'll keep improving the architecture, for example, add resource constraints to the architecture. And then up to this point, we'll just work within basic blocks. And then we start going across basic blocks to say, okay, how to schedule large regions. And in the same way, one technique to doing across large regions is trace scheduling. I'll get into trace scheduling a little bit. And then switch topics a little bit to figure out how to schedule loops, because a lot of times performance is mainly in loops. I will look at things like loop unrolling and software pipelining for loops. And then go a little bit into interactions with register allocation, how scheduling and register allocation interact with each other. And finally, conclude with scheduling done in hardware versus compiler, what are the trade-offs, and what's interesting things in there. So this is a lot of things, and hopefully we'll try to get to about halfway through in here today. So interesting thing is when we are compiling in a machine, so till now, most of the optimizations you guys didn't deal with the machine. They will run faster in any machine, no matter what. Okay, now we are kind of switching into, okay, now the compiler actually has to know about the machine and how to take advantage of what's happening in the machine. So you need to do that first. You need to understand what the machines look like. So the machine, basically a simple machine, fetches, decodes, and executes instructions and store results. That's what it does, one instruction at a time. And if you have so you go instruction after instruction. Sometimes when you have a branch, it might check the condition and might start fetching from somewhere else. So sometimes this pipeline gets stalled in a branch. So if you look at a very simple pipeline, this is things like 004 pipeline. You probably did this in 004. What happens is there are 5 stages. It's a fetch stage, get the next instruction, decode, find out what this instruction actually want to do, execute the ALU operations. Interesting thing is you only need the values from the previous calculation at this stage. So you can fetch and execute, decode without knowing any kind of dependencies. But now if you're using a result from a previous instruction, it will better be available at the execute time. And if it is, for example, if it is memory op, it might just calculate the address. You store it in the memory. And if you want to write back to the register, you write back at that stage. So this is basically the stage you go through. So in a normal, very simple machine, one probably did it in 004, you basically do instruction at a time. You go to all the 5 stages of one instruction. You're done with it, you do the next instruction. But this is very slow. So the way you get a lot of speed out of these machines is you actually pipeline them. So what you do is each stage, when you're done with the instruction fetch, before the instruction fetch will go into the next instruction before the rest of the stages of the previous instruction is done. So here, what happens is, oops, what happened? That's not the right button to press. Okay, I thought there's, okay, here's a laser. So what happens is, assume value produced by this instruction is going to be used by this instruction. And at that point, you can't just execute here because the data is not available until the write back stage. So at that point, there's a pipeline stall. So that's basically what happened in pipeline stalls. Okay? And so that's a very simple way. But when you go to real machines model, things get a lot more complicated. So for example, good old Pentium had a 5-stage pipeline, just like that. Pentium Pro had a 10-stage pipeline. Pentium, first Pentium 4 has a 20-stage pipeline. Now it's a 31-stage pipeline. So these things are growing by the minute. It's a much larger, deeper pipelines. So because of that, scheduling and getting everything right is a lot more useful and valuable in these machines. And other thing is different instructions take different amount of time. So if you do an add of 2 integers that from register and in a register, it's very fast. On the other hand, if you are loading from memory and doing a multiplication or a division, it can take a lot longer. So you need to know the length in there. It's not all same length. And what happens is in hardware, if the results are not available, pipeline stalls. So assume I did a division instruction and immediately use the result. And you look at it and say, oops, results are not available. I can't keep that executing that instruction. I just have to stall. So this is why instruction scheduling is very important. So there are other things in modern machines. There are multiple execution units in a superscalar type machine. If instructions are nicely sequenced, they can execute parallelly, get a lot of parallel performance. On the other hand, if there are dependencies, if the instructions are not placed exactly the right way, the machine can take advantage. It's not just only stall, it's just only few execution units can work in parallel instead of getting everybody to work. So it's even more important to have the right set of instructions in the right order. And what instruction scheduling does is basically we reorder instructions so that the pipeline stalls are minimized, and also you can get the maximum amount of parallelism. So that's basically what we are trying to do in instruction scheduling. So we can just go and keep reordering any instructions all over the place. There's you have to make sure that the original program behavior is maintained. So the way we manage to maintain original program behavior is looking at 3 different constraints. For example, data dependencies, control dependencies, and resource constraints. So there are 3 things you have to make sure that the program that you maintain in there. So data dependencies. What it means is if 2 instructions access the same variable, they are dependent. And you'd make sure that access pattern to that variable is maintained properly. So there are 3 types of access patterns, dependencies. It's called true dependency. True dependency means some guy writes to a variable, the next guy reads the variable. So you better make sure that the write happened before the read, and the read in fact get the value of the write. Otherwise, it's incorrect. There are 2 other types of dependence, ante and output. So since we have a small class, I'd like to see whether we can get a little bit discussion and interaction going on. So why is anti and output dependencies? I mean, are they fundamental? Why is there anti and output dependence? Okay, let's look at anti-dependence. So assume I read a variable and then I write it. Why do I have to maintain that dependence? So we have chalk here. Huh. Oh, okay. A lot of chalk. So assume I have something like just say A equals B plus 5 and B equals 3. Okay? So why do I have to maintain this dependence? Why do I have to do this instruction before this?
If you had the processor on write, I don't think this would happen with the 5-stage pipeline. Mm-hmm. It could be possible that since B equals 3 is such a simple statement, even though it comes later and begins execution, or it's fetched after the first instruction, it could be executed first.
Yeah, let's make, if you want to make complete, I can play 3 plus B. So here's the thing in here. The thing here is all these variables have some location somewhere. This is the location I keep B. Okay? The thing is I better read this value here before I overwrite it, because it's in the same location. It's a location-based dependency. So if I keep the value, if I want to, minute I do this instruction, finish it, this value is gone. I have new value here. And if somebody wants it, I can't just get rid of the value because somebody else is going to want it. So the anti-dependence means that if I'm actually using a value, I better have all the instructions I use that value done before I actually go and modify that value or get rid of the value. So how do you get rid of anti-dependence? Exactly, because it's basic. There's no real true use of the data, the value, but it just because it's both are trying to share the same location. Why don't I just, instead of B, I will just allocate a new location. I will say this would be B prime, which actually gets another block here. I'm pretty happy. I can reorder this. So output is the same. Output basically is, if I am writing twice, the last value has to survive. So you don't want to write in the wrong order and then the wrong value survives. But if you have enough mechanism, you can probably figure it out. Of course, if you're writing it twice and the first value is never used, you can say, wait a minute, why am I writing that? I mean, I'm just writing dead. Its value is dead anyways. I can get rid of that. So there are a lot of other things you can do, whereas true dependence is actually true. If somebody is using my value, I can't say, well, I'm not going to produce it, or I'll produce it later. I better produce it because somebody is waiting for me. Other things are basically artifacts of how we store things in memory and how we use that. So what happens is when two instructions are dependent, the order of execution cannot be reversed unless you do some kind of transformation I talk about. So what it does is it reduces the possibility of scheduling. So if there are two dependencies in this, we better maintain that order. So computing dependencies, basically what we want to do is, in basic blocks, it's easy. You just walk one instruction after another and say, okay, is there a dependency between those two instructions? And identify register dependencies are very simple. It's the same register. So if there are two same registers, okay, there's a dependency somewhere, okay? Things get subtle in other things. So for example, memory accesses can become arbitrarily complicated. So assume I do something like a base plus offset. Okay, I am getting from the stack. And at that point, it's like, well, am I getting the same stack location? Okay, this is something probably you guys have to do because you're putting a lot of things in stack. But you already know they are not dependent anyways, but from other information. But if you only know that I have accesses in the stack, I'll say, okay, I'm accessing from the stack pointer, therefore different locations I can look at differently. And then things get arbitrarily complicated when you go things like data dependence analysis. So for example, if I have two accesses, 2i and 2i plus 1, is there any value of I that these things could be dependent or accessing the same value? No. How about I and I plus 1? Instead of AI and AI plus 1, what happened? No, I mean, the thing is, what that means is if AI, what you write in iteration 1 is going to be the same location that iteration 0 writes AI plus 1. So at some point, some different iterations, all right. Whereas 2i and 2i plus 1, no iterations, because it's completely accessing different set of locations. So because of that, that's what data dependence analysis does. Grab these access patterns and say, are they overlapping? If they overlap, is there some pattern for overlapping that I can still take advantage of, stuff like that. And then things get even complicated. Interprocedural analysis. So assume I have a global and something get passed as a parameter to me, global variable. Are they the same? If A and B get passed as a parameter, can they be the same? And differing in the language definition. It could be the same unless you can prove otherwise. So because of that, you have to do globally. We can say, wait a minute, where did these things originated? What I get passed? And this can get arbitrarily complicated. And then you go into point alias analysis. So if you have two different pointers, are they pointed to the same thing? And in a language like Java, this is a very hard problem to solve. Because at some point it might, some point it might not. It depends on where it's coming from. It depends on all the paths and what different classes does and stuff like that. So this can start getting way complicated in doing that analysis. But this is what you have to do if you want to get the full level of analysis. For you guys, it's not that difficult because you don't have anything complicated in your programs. So you don't have to do too much analysis to do this. And so the key thing is how to represent these things. So the simple way to do is represent this dependence using a directed acyclic graph. Why is it acyclic? Why is it not an arbitrary graph?
If it was cyclic, then there's no first instruction.
I mean,
there's no. Otherwise, it's something else already happening.
I mean, yeah, exactly. If you can't have in a temporal ordering, we assume the program, what you're trying to maintain is the dependency in program execution. If you're doing temporal, you can't have cycles. I mean, that means you're violating the fact that there has to be sequential ordering to execute, and sequential ordering says there cannot be cycles in there. And nodes are instruction, edges are dependencies. So here's a simple program. So what I'm doing is I'm reading two different values out of R1 to R2 and R3, and I am adding R2, R3 and putting it to R4, and I'm using R2 to do R5. So the simple dependence is this. So what happens is instruction 1 produces R2, and both R3 and R4, instruction 3 and instruction 4 depends on that value. R2 is used in both instruction 3 and 4. And instruction 2 actually get R3, and instruction 3 depends on that. Okay, this is clear? So the one thing you do in this one is we put a latency number on each of these edges. The latency number says if the first instruction start on time 0 or clock 0, at what clock, the earliest clock that you have to delay the next instruction so that there's not going to be any stall. So assume both first, if you assume the 1 and 4 in here, I say delay 2. That means if I start the instruction 1 in clock 0, and if I start instruction flow in clock 1, I will stall it because I didn't have the delay of 2. So I have to start instruction flow in clock 2, because I need to at least have a delay of 2 because the value is not available in order for it not to stall. So we get this graph, and that gives us a notion about how much stalling you have to do. So here's an interesting thing. So I did a very simple change to this program. Can you see the change I did? Okay, what's the change I did? What I did was in 1 and 2, I used the same register R1, and here what I did was use R2 to get the next address. And do you see the change in the dependence graph that happened? Because now the R2, before you do the R2, what you have to do is make sure that the one get executed. Okay, so let me do a small modification to this one. So the second instruction, instead of saying R2 plus 4, if I say let me see whether this works. Okay. So instead of saying this is R2, if I say this is to be, say R, to be, we'll say R, we'll say 5. Okay, if I do that, what would happen to my graph? You see? So what you okay? We have answered that says this thing goes away.
4 has to happen after 2.
4 has to happen. Oh, sorry. I make it R6. Never mind. R6. I actually want to get 6. Okay, can't write it with this one, but okay. I make it R6. Some other register that's not here. What happens? So we have a one suggestion says, okay, 1 to 2 goes away. What else?
Might be other instructions not listed there.
So,
There might be other instructions after the 4th one that aren't listed.
yeah, but that's not even an issue. Like, think about instruction 1 and 2. Actually, you're right. Getting rid, because I was trying to do something. Okay. So So this is why what happens when you try to do a question on the run. Okay, so getting rid of this one, it looks like the previous one, yeah. I was trying to see whether there's anti-depend, but since it's 2 reads, it doesn't have anything. Okay, good. So you got it right first time. Do you see everything? So on the other hand, if there's a write in here, then you have to make sure that these 2 instructions, if there's a read and a write to memory, you have to maintain that there was anti-dependence. So I was expecting something, but it was not there, sorry. Okay, this one. What are my edges? Let's try to do that. What's the edge? Is there an edge between R1 to R2?
Yeah.
Why?
Because you can't overwrite.
Exactly. So there's an edge between R1 to R2. There's an edge in here. What else? How about R1 to R3?
Yeah.
R1 to R3, why?
R3 uses R2.
Oops. Okay. How about R1 to R4?
Yeah. Same reason.
Yeah. How about R2 to R3?
Yeah.
Yeah, because of R3 actually. Is it a true dependence or anti-dependence?
Anti-dependence.
Yeah, because this is reading it, this is modifying it, you better. R2 to R4?
No.
Nope. Okay. So, yeah, this is basically the graph you get. Okay, and I put some distances in there. So here I have a problem. Okay, so assume, so now you probably even know the answer. Assume instead of this being R1, if this was R6, what happens? You change the graph. This means I am reading the memory, so I am calculating the address. R4 has address. I adding 4 to that address location. I am reading from memory. Yeah, it's basically it's almost like a pointer dereference. Okay, sorry. Okay, so if I have R6 plus 4, what happens?
Remove the edge from the
Can you? So he's okay.
I don't
See,
think you can.
okay, so there's one thing. Can you remove this edge?
Because R6 could be R1.
R6 could be R1. If you can prove R6 is not R1, it's accessing 2 memory locations, I can remove the edge. But I don't have enough information to prove that R6 is not R1. This is basically what all the pointer alias analysis is all about. Because I am accessing 2 memory locations. Is it safe? Don't. I don't know at this point. And if R6 is R1, there's actually dependence in there. If R6 is not R1, I can get rid of that edge. So as you go into more real programs, you have to do all this analysis because otherwise there will be all these edges all over the place, because I don't know. And so that's the point I was going to do in the previous example, but this is actually the right one to do. Okay. So, so control dependencies are resource constraints. For now, let's ignore that. Okay, we will get to that hopefully later today or on next lecture. So, okay, so here's example program I am going to use for showing you what happens if when you execute and then go and show how to do some scheduling. Okay, so what happens is I put some number of cycles where the resulting register is going to be available, value in the resulting register. So load effective address into a register, it's 1 cycle, and the instruction 4, in what happens is here, I am doing a load from the, memory, because I am doing this off the stack pointer. At that point, it takes 3 cycles, because actually I do load from memory. This one, since I am writing to reading and writing to memory, I didn't actually put any value, because I don't have register value available at that. I'm not changing a register basically in this one. This one 4 cycles, because you have to not only just load it, you have to actually do AND operation also. So you have 3 cycles to load, 1 cycle to AND. So I'm just kind of making up these numbers. So at this point, okay. And this is a multiplication, because multiplications are expensive operations, so it takes some cycles. Okay? So what do you do? So what you do is, so first you take the first instruction. No problem, you can execute it. So when you look at the second instruction, what happens? Is there a dependency? There's a dependency first instruction because it uses the same register AX. Okay? And therefore, but the value is available in one cycle. So you don't have no problem, you can execute it here. Third instruction basically is not dependent on anything. I can just go and execute it. Look at the fourth instruction. It's not also dependent on anything. I can go execute it. Fifth instruction. Is it dependent on anything? Yeah, it's dependent on fourth instruction. How many cycles does it take for fourth instruction to have a value? 3 cycles. So if I execute fifth instruction now, what happens? It will stall for 2 cycles. So it has to stall 2 cycles, and the real fifth instruction happens in this cycle because the value is not in. So if you go to 6th instruction, there's no dependency, so it can go here. But 7th instruction depends on 2 instructions, 2 and 6. 2, fortunately, was done long time ago, the value is available. But 6, I'm just doing it, the value is not going to be available for 4 cycles, so I'm going to stall. And 7 in here. So this is what happens when you actually just naively keep executing. Because you execute something and the value is not available, things are going to stop. And this is not good. So this is the pipe stages you get. So this is when list scheduling come about. So the list scheduling is a way to go around and actually schedule so that we don't get the stalls. So algorithm is simple. So the idea is you do a topological sort of this dependence DAG. And then you have to consider instructions that can be scheduled without a stall. Because you have a bunch of instructions that can be scheduled. And if this instruction don't cause a stall, you go and schedule it. So you go down the line here. And however, the optimal is an NP-complete problem. Because what that means is a lot of times you have choices of which instruction to select. If you select the wrong instruction, you might not end up in the optimal schedule. You can get into stall situation. Okay. There might be cases that no matter what, there will be some stalls, but how to minimize that is the question. So here's a simple algorithm. You do a topological sort. You have a ready list. That means all the instruction right now that doesn't have any dependencies. That means all the predecessors that has a dependence already been scheduled. So I can actually run that instruction now. That's in the ready list. And the thing is, you have to pick up one from the ready list, put it in there as a next instruction. And the minute I schedule something, bunch of other instructions might be also schedulable because you are depending on that one, and the minute you schedule that, so you put those into ready list and you iterate. The question is, when you have multiple things in the ready list, how do you pick? So if you have multiple instructions on the ready list, what kind of heuristics can we use to pick one?
How long?
You might want to put a memory load in there so that other instructions, when they come later, they'll already have a memory load.
Yeah, so that's an interesting, good one. That says if that means you want to bias loads to go first because load means somebody is going to use it anyways. You might as well put it there. That's a good one. What else?
How long an instruction's been on the ready list?
That's an interesting one. To how long? Because that means if you put ready list, just edge it and then get it there. Anything else? So here are the 3 things that normally being used. Pick instruction with the longest path to the leaf node. Because that is the one in the critical path. That means you need that value to get the next value to get the next value in there. And so if it takes the longest path to the end, you better get that path done fast. So if there's something in the longest path, get that first. If there are multiple things in the same longest path, get something similar to what you said, but get an instruction that will get has lot of successors. Because that means the minute you get that, you put lot more things in the ready list. If you take something that doesn't add anything to ready list, you are reducing your schedulability. Get things that are actually being used multiple times because you want to get those things fast to get more instruction executed. Other thing, a little bit similar to is if there are multiple pipelines choose something that can shove into a less busy pipeline. So get those things, pipelines filled up fast. So this is in a superscalar type thing. So to do these things, so the first thing is to pick longest path to the leaf. Okay, doing that. So you can do a simple algorithm to calculate the longest path to the leaf. The other thing, calculation is the number of successors. So for each node, we'll calculate the longest path to the leaf, the number of successors. So here's a small program. I will just do this by example. That basically is previous program. I actually added 2 instructions in here just to finish it up. And so here's the dependence graph, DAG. So in here, here's a DAG for this one. So there are some large clump of instructions that are actually together in here, and there's this another 2 small clump, and this guy just not dependent on anything. So the first thing you want to do is to calculate the depth. So the things that are there's nothing dependent on this, the depth is 0, because if I mean if you execute it, that path is done. Okay, and then what are other places? What's the depth? What's the depth of this one? 3. Okay, I think I have that one next. What's the next depth you can calculate? Depth 3. Okay, I think we got that. Okay, and then what? 4. And yeah, I see. Okay, now you got the thing. This has 7, this has 4, this has 5. Okay, simple. Just calculate it out. You can do that, all the information available. And then you get the fan out. So most of the things in the fan out 0, 1. You get the fan out in here. And then you get to the fun part. So now what you have is what's in the ready list. What things are ready to execute right now? 1, 3, 4, 6. Yep, you get 1, 3, 4, 6. And if you order in this my order, 6 comes 6, 1, 4, 3. So 6 has the highest depth, 1 has the next, 4 has the next depth, and 3 has the last. So I got that order. So what I do is I get the 6, schedule 6 first, no problem in there. Then I have 1, 4, 3. I get 1, I can schedule 1, no problem there. And then the minute you schedule 1, 2 becomes available. Okay, because now the dependency, so I can put 2 into the ready list, and 2 goes to top of this. So now what I try to do is, okay, trying to schedule 2. And need try to schedule 2, I look at my dependencies, because 2 is dependent from 1. But since the distance is 1, I can go and schedule that, because there's no problem, it can do it. And then minute I do 2 and 6, I actually put 7 into the ready list. 7 goes on the top. So if now I can do is try to schedule 7 there, and if you look at 7, what are the dependencies to the 7 from where and where? The 7 depend on from 2 and 6. So from 2 and 6, I have dependence. 2, the dependence is 1, I am done. But 6, I have to wait 4 cycles, but I have only done 3. So now I can't schedule it there, because if I schedule it, I am going to stall. I had to put a stall. So because of that, I had to give up on 7. I look at 4, and I have no problem. I can do 4 now. And the minute I do 4, I add 5 into the list. And then now I can pick up 7. Can I do 7 now? Yeah, I can do 7 now. I put 7 in there. And then the minute I do 7, I get 8 and 9 into the list. So can I do 3 now? Yeah, no problem in here. And then I get 5. I can do 5. There's no problem. Let me see if they can do 5. Yeah, from 4 to, I have 3. I have already done 3. I can do 5. I pick up 8. Can I do 8? Yeah, I can do 8. Can I do 9? I look at 1. I can do 9. So at this point, I get my schedule in here. And in basically to schedule that, it took 9 cycles. Compared to if I just do a naive run in the schedule load of 14 cycles, because I had a bunch of stall slots in here. 5 stall. You avoided 5 cycles of stalling by doing that. So this is a very simple way. We did some reordering of instructions. But by doing that, we actually make sure that we have a very tight schedule. This is the very simple, basic way. I mean, the key thing is there are a lot of heuristics you can do. You came up with a good heuristic. There are a lot of these things. There's no set saying this is not provably correct because this NP complete problem. So as you look at, people have developed heuristics over time, and this is a good set of heuristics. Okay, any questions so far?
What if all the nodes in the ready list would cause a stall?
I have no, at that point, you just have to figure out the easiest stall or the minimal stall and do it. I mean, you will have a situation, and then especially they don't have that many things in the release, it's going to stall. But this is where it might be non-optimal. There might be optimal schedule if you do something differently with the global knowledge that you can do without stall. But since we are doing this very local algorithm, you can run into stalls. Yeah, it doesn't guarantee eliminating stalls. So the next thing is, modern architectures are a lot more complicated. It has a lot more resources. It's not just one thing at a pipeline. So you can run parallel operations, but with some constraints. And so if you have parallel operations, you actually want to take advantage of that too. So here's a very simple example. So assume I have two different execution units. One, I do only register to register operations. So no memory operation involved, and I can get everything done in one cycle. And the other one, if I'm doing register to memory operation, memory to register, register to memory. So I'm reading from register, putting it to memory, or vice versa. And assume if I'm loading, it takes 2 cycles, and I'm storing, it takes 1 cycle. So if you have to look at this very thick book of architecture in each architecture to figure out all these numbers. I mean, how many cycles things take. So in here, so each pipeline, you can represent the superscalar with multiple pipelines. Before I only one pipeline, each pipeline with some set of resources. And so for example, here what I do is the first ALU pipeline, register to register, I put this ALU. And register to memory, I put these 2 because it can have 2 cycles. So I put these 2 different pipelines in there. Okay, and then what happens is now I modify this algorithm a little bit to say now when I'm scheduling it, it's not just going to the pipeline. I have to figure out the right pipeline and figure out all the precedence constraints in there because all the dependence maintained and plop it in the right place in the pipeline. Okay, so here's the same program again. Now I change my dependencies a little bit because to make the life easier for every one of us. So now I have my D numbers, distance from the bottom, and fan out numbers, and I have my ready list in here. And so what happens is now I pick up the first instruction. It's an arithmetic instruction. It's going to the ALU pipeline. Put it in there, no problem. And the minute I do that, I can add 2 into the list. I put 2 in the first because it has the highest distance in there. Now when I pick up 2, what type of instruction is that? It's a memory operation. So it's actually memory read. So it has to go into this pipeline, memory pipeline. Where can you put that? I'll do this one, I'll ask this. So the first thing is, it also dependent on 1. So because of that, only 2 can go only on these 2 because the first instruction has to be done before 2 is done. 2 is started. Since it's 2 cycles, it goes from in there, so that the value is available in here. Okay, and then you take the third instruction, which is sixth instruction, which is what? Which is arithmetic op. Where can I put it there? Is there dependence in there? Where can I put it?
Put it in the ALU.
So here, you can put it in here. So you put it in here. Okay, and then that makes you put 7 into this thing. And when you pick up a 4, 4 is also load operation. Where can you put 4? Here? Why not here? Because I have no dependence in there, I have some available slot. Put it in there, so I can put it in that one. Doesn't need. So now I have done reordering in here because I realize I have this early slot without dependence. Just plug it in here, and what that means is I make 5 available in pipeline. Pick up 7. 7 depends on 7 is integer operation, depends on 6 and 2, and you have to put it in here because the 2 has to be done before you can put it there, and then that makes 8 and 9 go in, and the next one is 3. 3 is arithmetic operation. I can put it in here because there's no dependence in here. And 5 depends on 4. So 5 is a store operation. It goes here. 8 depends on 7, so it goes here. And 9 depends on 7, but it's a memory operation. Now, so it goes parallel with 8. So do you see that how this works? So we have this, all these things got packed pretty nicely. So this is my final scheduling for this one.
What would be the actual linear order that you would write out instructions?
Aha, that's interesting. In some sense, you probably want to do 1, 4, 6, 2, 3, 5, 7, 8, 9. Because, for example, in superscalar, the architecture will figure it out, and then if there's parallelism, do. On the other hand, if you have something like a VLIW, you have to probably explicitly say that, because VLIW doesn't automatically try, architecture doesn't do that. You have to explicitly say for the execution unit, ALU unit, here are the instructions, and memory unit, here are the instructions, parallel bundle. So for example, if you look at Itanium machine, you have bundles of instruction. So this is my first bundle, 1 and 4. My second bundle is 6 and 2. My third bundle is 3 and 5. My fourth bundle is only 7. There's no op in here because there's nothing to put in that bundle. And my fifth bundle is 8 and 9. So you actually give explicit bundles in there. Say in the first one go to first unit, and the second memory op goes to the other unit. So if you have the architecture, so something like that, you have to actually do that. So let's see how far you can push this one. Scheduling across basic blocks. So what we did was we scheduled each basic block at a time. But it will be fun because the basic block can be small, and that means you don't get that much freedom, that many instructions to schedule. You don't have a large of a ready list. You can still have stalls. So if you want to get better quality, you want to actually go across basic blocks. So yeah, number of basic blocks, instructions in the basic blocks is small. The key thing about going across basic blocks is there are controls, branches. So how do you have to actually schedule across control branches, handle control branches properly? So what does it mean? So assume if you want to move instruction from above to below. Okay, so I have an instruction from A that I want to move to, I had to move to both B and C. But can I move to B and C? Can you move to C? No problem, because if control goes to A, it will go through C. Can I move to B? Not really, because there's a path that can reach B without executing A. So if I get an instruction from A and move it to B, I might actually come from somewhere else and executing extra instruction there. And that's not doable. So you have to make sure that if I move instruction, that it's always the same path happens, because I can't come from somewhere else in there. It's real joins happening. You can't do that. The same way in here. If I want to move instruction up, I want to make sure that instruction always get executed. So from B to A, of course, there's a path always. But on the then C to A, there might be a path from C that doesn't reach A. So if I execute instruction, that either it's wrong if I actually change state, or it's more work because it will never actually get executed if you go the other path. So it's not just, you can't just keep moving things up and down. You have to have a lot of correctness properties. At worst case, it's a correctness issue because you will write a wrong value. In the normal case, it's just extra work. You just do work without just really requiring to do that. So these control dependency constraints what you can move across blocks. So there are other interesting things. So assume there's no control so I am doing something like this. So there's no really data dependence because this condition doesn't write anything. And assume condition is not a condition on A. Can you move things up? So assume I have a condition which can read B and C. Can I move A equals B op C up out of that condition? What do you think? Conditions can't write. I'm saying it's not even reading A, it's only looking at B and C. Can I move it?
Sorry.
No problem.
If you move it, does that mean get unconditionally executed.
Yeah.
And you can't,
Why?
because then it'll get unconditionally executed.
Yeah, I mean, what's the reason? Assume you just.
Well, it's wrong.
So here's a possible process. So I'm trying to move it here. How about my condition is C not equal 0 and do a division? So you look at it and say, hey, there's only read dependence, there's no data dependence in here. But actually, you really have to maintain that because if you actually do that condition, and I'm going to just do divide by 0 otherwise. So things like that. And so in most cases you can't do so. So here, I mean, if I'm checking if there's a valid address, I can't. So you're moving across branches, you have to be very careful. Okay, that's the moral of the story. I mean, it's not just simple dependence test. There might be a lot more other things involved. That is not a simple test.
So does this movement happen at the scheduling stage, or would it happen at the earlier stage of optimization?
So a lot of things we do earlier stage, we actually do analyze and move in some sense. We might do some things like data flow optimization can move something in there. So I'm trying to see how we can do some movement in the scheduling stage. So data flow optimization, you probably have to validate whether it's doable. So one thing you can do, one thing people have done, it's not a class project, but is a thing called trace scheduling. This is a popular technique. What trace scheduling does is it finds the common path across a large part of the program. Okay, and it combines these basic blocks of the common path to one single path and get a much larger block to optimize. So, and then you need some cleanup code because if you exit the path. So let me give you examples. So assume I have a program like that, a bunch of basic blocks, conditions. And you realize most of the common path is this. You can do some kind of profile feedback or the user tells you this is the common path. The other two are uncommon. So what you can do is you can basically take the uncommon things out and put it in here and basically create a nice large gigantic block. But still there are problems because there are control going in and out of the block. You can't move things around that much. So one thing a trace scheduling does is try to create blocks where there's a single entry and multiple exits. Okay, because multiple entries create problems, but single entry, multiple exits, and then what you do is each exit basically try to do compensation code unless you exit from the bottom. So in order to do that, what you have to do is assume a piece of code like this. You can actually do some duplication. So if there are join, instead of really joining and going to one pass, you can actually duplicate a piece of code. And after you duplicate, what happens is you can optimize each branch separately. So in here, what happens is you can duplicate the exits out of each of the branches. So assume we go that branch and here's the code sequence in there. If you go this branch, there are repeated patterns. But now what happens is you created this middle block where you have single entry and only multiple exits in there. So I can do a lot more optimizations in that. So I give a lot more freedom to move code around that because what matters in the main block anyway, because this is where we know most of the time we are running. And by doing that, you can get this large block, you get a lot more opportunities to move instructions around. And sometimes you can even move things across these. So assume I move an instruction that is, oops, you can't really see the exit. So here's exit in here. Assume there's exit here. There's exit here. There's exit here. So assume I move an instruction from here to here. Sometimes you can even do it, but if you do it, you might have to put some correction code into F. So that means I do some thing, but on the other hand, if you do G's instruction and then do this exit, then I have to go and fix it up here. Since these things are not run that often, it's okay to do fix up because it do a lot more work in there. Because once in a while you do that, it doesn't make that much of a difference. So by doing this, you can actually do a lot of get much larger scheduling regions. Okay, where are we? Okay, so I want to stop here, and in the next lecture, start focusing on loops and loop optimizations. So I hope everybody had a good time in the last project. A lot of optimizations. Code runs fast. Can you see it actually running faster? What is generating?
We didn't really have test cases that
actually check.
Okay, yeah, yeah. But I mean, the interesting thing is, as we said, you did all these stupid things in the front end. You created code that looks really ugly. But now, after these doing optimization, they should start looking like the intelligent code that you would have written by hand, instead of all the dumb code that get generated in there. So sometimes it's fun to actually look at the code generated and say, wow, that's an interesting thing. I would have never thought about it. A lot of times when you combine these multiple things, and then you go to the original program and generated code, sometimes it can even surprise you. So it's fun. Good. So what I'm going to do next time is finish up scheduling. And then the next lecture going to be on register allocation. And then finally, then next week we are going to do trying to put everything together and basically close the course. You're almost at the end. Okay, good.